Hi everyone, welcome to another session of the HBL files. In today's session, we will be solving problems about the other forms of inverse proportion. Let's begin. For the first one, for each of the following questions, state the two variables which are inversely proportional to each other. Remember that the general formula for an inverse proportionality will be y is equal to k over x, where k is a constant. And although y and x can be replaced with any other variables, as long as these are their relative positions with respect to each other, then they are inversely proportional to each other. For the first equation, we have y is equal to 3 over x squared. This can be read as y is inversely proportional to x squared. Next, y is equal to 1 over square root of x, which can be read as y is inversely proportional to square root of x. Next, y squared is equal to 5 over x cubed. We will read this one as y squared is inversely proportional to x cubed. The fourth equation, n is equal to 7 over m minus 1, which can be read as n is inversely proportional to m minus 1. And the last equation, q is equal to 4 over the square of p plus 1. We can read this as q is inversely proportional to the square of p plus 1. Next question. If z is inversely proportional to cube root of x and z is equal to 5 when x is equal to 64, find the value of z when x is equal to 216. Just like what we did in solving direct proportion problems, we will begin the solution by writing the general equation for this scenario. And that is by converting this phrase into a mathematical statement. Z is, so Z equals, inversely proportional k over this variable, cube root of x. Next step is to solve for the value of k. Manipulating this equation, we will have k is equal to z times the cube root of x. We then substitute the initial values given to us. Z is 5, x is 64. If you're not familiar with the cube root of 64, you can express 64 in terms of its prime factors, giving us this. Finding the cube root of 2 raised to 6, you can simply do that by dividing its exponent by the index, giving us 5 times 2 squared. 2 squared is equal to 4, and multiplying that to 5, we have a value of 20 for k. We can now replace the k here by this value, giving us z is equal to 20 over the cube root of x. We can now solve for the value of z when x is equal to 216. Now, finding the cube root of 216 can be difficult for some. So we again express this in terms of its prime factors. Now, notice that the sum of the digits, or the sum of these digits, will be equal to 9, which is divisible by 3. That means this number is divisible by 3. If you divide 216 by 3, you'll get around 72. And 72 is a much more familiar number to us because it's 9 times 8. Finally, we can express its prime factors to be 2 cubed times 3 cubed, which again allows us to simply get the cube root of these numbers, giving us 20 over 2 times 3. 2 times 3 is 6. Reducing 20 over 6 to its lowest term, this will give us a value of z of 10 over 3. Now, let's look at the inverse proportionality concept. Notice that the x values underwent an increase. So if we look at their cube root values, so the cube root of 64 is 4. the cube root of 216 is 6. So in the variable cube root of x, it experienced an increase in its value. So for the z value, we should expect a decrease. The initial z value is 5. The final z value, or the second z value, is around 3.3, which is smaller than the initial value. So our results, or our result, is consistent with the concept of inverse proportionality. Next, if q squared is inversely proportional to p plus 3, and q is equal to 5 when p is equal to 2, find the values of q when p is equal to 17. Let's begin with the general equation for this scenario. Q squared is inversely proportional, so k over p plus 3. We then solve for k by manipulating the equation and multiplying q squared to p plus 3. We substitute 5 for q and 2 for p, giving us 25 times 5, or simply 125. Substituting 125 to k, we have q squared is equal to 125 over p plus 3. Next step is to find the values of q when p is equal to 17. So let's substitute 17 to p, giving us 125 over 20. And then let's find the square root of each side. But before that, we can actually simplify this fraction over here. Notice that they have a common factor, meaning the numerator and the denominator will have a common factor of 5. So dividing the numerator by 5, this gives us 25. And dividing 20 by 5, it gives us 4. Then let's proceed in getting the square root of each side. This will give us q is equal to plus minus 5 halves. Notice that both 25 and 4 are actually perfect squares. So this means that when the value of p is 17, the q value can either be positive 5 halves or negative 5 halves. Next, given that t is inversely proportional to s cubed, copy and complete the table. So again, let's begin with the general equation. T equals inversely proportional k over this variable, s cubed. Solving for k, we have t times s cubed. We can make use of these values to solve for k. Substituting 80 for t and 1 for s, 1 cubed is simply 1, so the value of k is 80. We now have t is equal to 80 over s cubed. When s is equal to 2, let's use this equation to solve for t. Substituting 2 to s, we have 80 over 2 cubed, or 80 over 8, which reduces to 10. That means when the s value is 2, the t value will be 10. Next. When the s value is equal to 4, we again make use of this equation. And substituting 4 to s, we now have 80 over 64. Remember, 4 times 4 is 16, and 16 times 4 is 64. Now, you might notice that both the numerator and denominator are actually divisible by 8, giving you 10 over 8. But we can further simplify this to 5 over 4, or 1.25. So when the s value is 4, the t value is 5 over 4, or 1.25. Next, here we are asked to determine the value of s when t is equal to 0.08, or 0.08. So I'll be isolating s cubed by manipulating the equation, giving us 80 over t. Substituting 0.08 to t will have this fraction. If you have your calculator, you can immediately solve this. But if you don't, you can actually opt to express this denominator into its fractional form, which is 8 over 100. Simplifying this mixed fraction, we can do that by multiplying the numerator by the reciprocal of the denominator, which is 100 over 8. Now, notice that 80 divided by 8 is 10. Multiply that to 100, that gives us 1000. We then get the cube root of each side. That will give us s is equal to 10. That means when the t value is 0.08, the s value will be 10. And for the last value in this question, when t is equal to 0.01, we can substitute that to the t value in the formula. Again, we can express this into its fractional form. That will be 80 over 1 over 100. And simplifying this mixed fraction, this gives us 80 times 100 over 1. We now have s cubed is equal to 8,000. We then get the cube root of each side, but it will be simpler for us if we can express 8,000 to these factors. 8 times 1,000. Because here, both 8 and 10 are perfect cubes. We now have s is equal to 2 times 10, because 2 is the cube root of 8 and 10 is the cube root of 1000. 2 times 10 is equal to 20. That means when the t value is 0.01, the s value will be 20. So as you can see, as the s values increase, the t values are decreasing. Okay, for the last problem, for a fixed volume, the height h centimeters of a cone is inversely proportional to the square of the base radius r centimeters. Cone A has a base radius of 6 centimeters and a height of 5 centimeters. The base radius of cone B is 3 centimeters and the height of cone C is 1.25 centimeters. If all of the cones have the same volume, find the height of cone B and the base radius of cone C. Okay, so let's begin this problem, or let's begin the solution to this problem by, of course, writing the general equation. Now, look at this one. H is inversely proportional to the square of R, which is basically this. Now, let's first solve for the k value. We have h times r squared. Notice that here in this scenario, our first, second, and third conditions are actually the cones A, B, and C. Now, our initial condition for cone A will be a radius of 6 centimeters and a height of 5 centimeters. So let's substitute those values here. A height of 5 centimeters and a radius of 6 centimeters. Squaring 6 centimeters, we have 36 square centimeters, and multiplying that to 5 centimeters, we have a total k value of 180 cubic centimeters. Now, notice that in the calculation of k for this problem, I included the units. Why? Because I want to show you guys that this k value actually includes the volume. Because in this problem, we have 3 variables involved: the volume, the height, and the square of the radius. Since we are comparing only the height and the square of the radius, we must be able to set this volume constant. And as you can see, the volume is actually part of this k value. Again, I'm not saying that this is the volume, okay? Because of for those of you who are familiar with the volume formula for a cone, you'll know that there's an additional factor, okay? But then again, I just would like to show you guys that the K value actually includes the volume of the cone. So replacing the K value by 180, we have H is equal to 180 over R squared. This will now be our equation for the next two scenarios, for cone B and cone C. Solving the first question, the height of cone B, we apply this equation. And since we're given with 3 centimeters as the radius, we can substitute 3 to R, giving us 180 over 3 squared. 3 squared is equal to 9. 180 divided by 9 is equal to 20. And don't forget the unit, centimeters. So for cone B, the height will be 20 centimeters. Now, let's compare the values of the square of the radius and the heights for cones A and B. So for cone A, the square of the radius is 36 centimeters squared. For cone B, the square of the radius will be 9 square centimeters. So 36 became 9. So there was a decrease in the value of R squared. That means we should expect the value of the height to increase. Now, the value of the height for cone A is 5 cm. And the value of the height for cone B is 20 centimeters, which is consistent with the inverse proportionality concept. Next, let's solve the second question. The base radius of cone C is what's being asked here. So let us isolate R squared, giving us 180 over H. We then substitute the value of H to be 1.25. So 180 divided by 1.25, you can immediately get the answer using the calculator. If not, you can express it using a fraction. 1.25 is 125 over 100, or in lowest term, it's 5 over 4. We then simplify this mixed fraction over here. This gives us 180 times 4 over 5. So 180 divided by 5 will be around 36. And then 36 multiplied by 4 will be 144. Getting the square root of each side, we'll now have R is equal to 12 centimeters. Again, let's check for the inverse proportionality concept. The height of cone A is 5 cm. The height of cone C is 1.25 cm. So the height underwent a reduce in values. So we should expect the square of the radius to increase in value. The square of the radius in cone A will be 36 centimeters squared. And then the square of the radius in cone C is 144 square centimeters. So again, it is consistent with the inverse proportionality concept. So that's it. That's how we solve these other forms of inverse proportions. I hope everything's clear, and thank you for learning with me today. See you in the next session of the HBL files.